All right, we're going to talk about sets in the first section. And sets are a collection of objects. I collected baseball cards growing up. Nobody does that anymore. But I had large sets, and you would try to get the whole set from a certain year and a certain maker. That was the thing to do. And with us and a set, what's going to be the object in our set? Normally going to be numbers. Okay, that's the objects in our set. Are numbers of various types, and we'll get to those types. If I say the word elements, it's a piece inside of a set. Okay? And need to get a Greek letter there. It's a Greek letter, lowercase epsilon. If you've never seen that before. We'll use that word to mean something is an element of something else. So element means it's part of it. It's inside of that. So elements are parts of that. So it's kind of like the John Smoltz rookie card was a piece inside of the Topps baseball card set from the year 1991. So that was a good set. It was a Detroit Tigers card, wasn't a Braves card. But anyway, that was a good set for that. Now, the way sets are done is with set braces, and set braces are the curly braces. Is maybe what you've called them before, curly braces. One on each end there is a set brace. So, an example of a set. We'll call this set. We'll name it S for set. And it might have some numbers in it like 1, 2, 5, and 7. I just made those up. Not any real rhyme or reason to why I picked those numbers. Just pick some numbers to be in that set. Okay? Now, that's our set. All of these pieces on the inside, the 2, the 1, the 5, and the 7, are elements of that set. Okay? So I could tell you that 2 is an element of S. That would be the notation for that. 2, and then the lowercase epsilon, S. 2 is an element of S. That means 2 is inside that set. And it is. It's right there. Okay? So we could have elements of that. So 2 is an element of S. Is how you would read that. That's how that's read. Okay. Now, what about the number 3? Is it in that set? No, it's not there. So it's not an element. So the notation for not an element is to take the epsilon and then put a slash through it. Cross it out. Say not an element. 3 is not an element of S. Okay. So anytime we want to say something is not an element of or not equal to, we just put a slash through that, the symbol that we're using, okay, to say it's not. All right. All right. When we're talking about sets, there's 2 different kinds that we'll deal with in here. One is called a finite set. And the other kind is the opposite of that, is an infinite set. Two very different things, but they're both sets. A finite set has a limited number of elements. You could count how many are in there. That's kind of what I think about finite. Finite means you can count them. There's only a certain number of them in there. It's a finite number, meaning it's countable. You can say there's only these that are in there. It's got a stopping point. An infinite set has an unending or unlimited number of elements. You couldn't count how many are in there. You might tell me what kind of things are in there, but you can't. There's not a stopping point that says, oh, it's only the numbers 1 through 9. That would be a finite thing. Okay. All right. So let's look at some various examples of finite and infinite sets. Okay. One set that we deal with in here is those numbers 1, 2, 3, 4, 5, and so on. The dot 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 means keeps going, right? If it keeps going, is that finite or infinite? Infinite. That's right. Dot 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 means it keeps going. Now, what kind of numbers are those? They're the natural numbers. And the notation for that is that. It's the natural numbers. Natural numbers. The way I think about that, if somebody asks you to count how many beans are in the soup, you'd start with number 1, right? And you count 1, 2, 3, 4, that sort of thing. So that's natural. So that's why they're called the natural numbers, because they're the counting numbers. That's how you count. Okay. All right. Let's look at this set. 1, 1/2, 1/4, 1/8, dot dot dot. Is that a finite or infinite set? All right, so we know that the natural numbers was infinite. This one, why would this one be infinite and not finite? It is infinite, that's true. But why? Right, so what's happening here with the numbers? We're going 1, and then we got 1/2, we got 1/4, we got 1/8. What would the next one be? 1/16 and 1/32, 1/64, and 1/128, and keep going. So you're doubling that number that's on the bottom every time. That's really all you're doing there. So, but it just keeps going. And the dot 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 tells us that it's infinite. Okay, so be careful. That dot 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 on the end tells you that's infinite. That's important. Okay. Let's look at this set. 7, 8, 9. Dot 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 15. What kind of set is that? It's finite. It's got a dot 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 in it though.
But there's another number after it.
But it's got an ending point. That's right. That number after it says, oh, we're going to stop at 15. We're going to start at 7. Get all these integers that are in between 7 and 15. That dot 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 inside of there says, that's all those numbers that we don't want to write down. They're in there. And this is a finite set. So this is finite. Because it ends, has an ending point. Okay? All right? Let's look at another way they might give us a set. And that's this set builder notation is what it's called. And I don't know if you've seen this in high school or not. You may or may not have. If you haven't, it's not too difficult to understand. If you have, maybe if you understood it, great. If you didn't, maybe we can make you understand it. Okay? So you have an X, and then we got this straight up and down bar. That means such that. And then whatever we write after this tells us what X is.
Hold on, it means what?
Such that. Such that. X such that.
I don't know what I thought you said.
I have no idea either. 9 less than or equal to X less than or equal to 13. X is between 9 and 13. That's the way that reads. 9 is less than or equal to x is less than or equal to 13. So that means x is between 9 and 13. So could you tell me all the numbers that are in that set? What are the numbers that are in that set? Okay, I agree with that. 10, 11, and 12. He left some space for a reason. Why are 9 and 13 both included? Yeah, because it's or equal to. Right there, you got the equal to marks there, so they're included in that. She's right, absolutely. Good job. So that's another. They wrote the set this way. That means the same thing as this, right? They're the same thing. Okay, is that finite or infinite? Finite. It's got a starting and an ending place, so that makes it finite. So we know that. Finite. All right, good deal. Let's try to do this. Let's try to list the elements in each set. So those are our instructions to list the elements in each set, and then I'm going to give you an example with some sort of description of the set. Okay, and I'm going to use that set builder notation. X, as long as X is like whatever I'm going to write here. X is a natural number less than 7. So we're going to try to write that set and include all the numbers that exist in it. So what's a natural number? Counting number. So this tells us it's a natural number that's less than 7. So what counting numbers are less than 7? 1 through 7. Yeah, 1, 2, 3, 4, 5, 6. And then is 7 included here? No. So we go 1 through 6. So we could write it 1, 2, 3, 4, 5, 6. I would even accept 1, 2, ... 6. Most of us are going to do that since it's a pretty small set. That's what most of us are going to do. But understand that means the same thing there. Okay? So we listed the elements in that set. Good job. Let's do another one. X such that X is a natural number greater than 7 and less than 14. Greater than 7, less than 14. What are the numbers that are in that set? 8 through 13. 8, 9, 10, 11, 12, and 13. Absolutely. That's our set. Listed all the elements of that. All right, let's get a couple of definitions here, and then we're going to start doing a little bit of set theory with this stuff, talk about subsets and empty sets and that sort of thing. So one thing we need to define is what's called the universal set. And kind of the layman's way of describing that, and maybe that to me makes the most sense, is it's everything that's in the discussion. In our case, it'll be everything that's talked about in the problem. So if they're saying, something's part of the natural numbers, then the natural numbers would be our universal set for that particular problem. So the universal set can change depending on the problem that you've got. So that sometimes I may talk about the natural numbers, sometimes I may talk about the integers or something like that. So it changes. But that universal set is just the bigger umbrella that covers the problem. That's what we want to, if they refer to the universal set, that's what they're talking about. Okay? Kind of the opposite of that, what's called the null set. It's an empty set. Well, if it's empty, it has no elements. There's nothing in it. So it would be a set of curly braces with nothing inside of it. Or a circle with a slash through it means the same thing. So those two notations for the null set. Either empty braces or a circle with a slash through it. Both of those mean the null set. That means there's nothing in the answer there. Okay? There's not a universal set notation there because the universal set can change depending on the problem that we're dealing with. Okay, so we don't have any kind of special notation for that. It just depends on what the problem they give us is. Okay, so the null set, empty set, it's got nothing inside of it, so it's empty braces or the circle with a slash through it. It's the same thing. All right, next thing is a subset. A smaller group of elements from a larger set. Okay, so think about this classroom. You've got all you guys sitting in here. These two gentlemen at this table would be a subset of our full set of students. All right, so that's what subset is referring to. So when we talk about a subset, we're talking about pieces of the original larger set. It doesn't necessarily have to be the universal set, but it's just pieces of a larger set. And there's such a thing as a proper subset and an improper subset, but we don't get that deep in here. If you go into, anybody's going to take number theory later on, you might need to know that, but I don't know if anybody's going to do that in here. Unless you plan on changing your major to math. Is anybody going to do that? I've had very little number theory, enough to know that I didn't want any more of it. So let's look at an example or two. Okay, so let's say we have a set, and we'll call it set A. Okay, so this is the givens in the problem. These are the problems that we have, and set A has the numbers 1, 2, 3, 4, 5, 6, 7, and 8 in that set. Set B, another part of the problem, has 2, 5, and 7. Now, I want to know, is B a subset of A? Is B a subset of A? So, what are the elements of B? 2, 5, and 7. Are 2, 5, and 7 in A? Yes. So, is B a subset of A? It's a smaller group that all of the pieces were inside of a larger group. So, yes, B is a subset of A. So, we could say yes to that. Now, let's learn a little notation that goes with that. Okay? To say that B is a subset of A, the notation, it looks like a capital C, but then you put a little bar underneath it so that you know it's the subset symbol. Okay? That says B is a subset of A. That's what that says. That's how that reads, maybe. B is a subset of A. And I'll try to scroll more toward the top there so you guys can see better from the back. Okay. B is a subset. So it's like the C. It's more of a U shape than it is a capital C, but I always end up making it look like a capital C. I've tried to not make it look like a capital C, and over the course of life, I've not been able to do that. So just had to be one thing I couldn't do, and that was it, maybe. I'm just kidding. All right, so let's look at another one. Let's take the same set A. So I'm just going to copy that. So if you want to, just say, hey, that's the same set as A. And I want to look at set C. 10, 15, 20. Is C a subset of A? So I'm using the notation to ask that question now, instead of writing out the sentence. Is C a subset of A? No. So our statement could be that C is not a subset of A. So to say that mathematically, C not a subset of A. So you write the subset symbol and then slash it. Says that's not a subset of A. Asterisk symbol there, kind of an important side note here. The empty set is not a subset of any set. No matter what your original or your universal set is, the empty set, it doesn't contain anything, so it cannot be a subset of that. That's kind of one of those questions that they like to ask. It's kind of odd because it's never a subset of that. But that's kind of a theory thing, where this is the ideal situation. Subset is not, or the empty set is not a subset of any other set. So make sure you know that. That's very important. Has anybody ever seen Venn diagrams? Been familiar with those? Been a while, maybe. Tend to use them a lot. Maybe elementary school uses them quite a bit. We kind of got to, at my high school, started using things called thinking maps, and Venn diagrams are part of that. And really, Venn diagrams can help with set theory a whole lot. So let's say we had a Venn diagram, and we'll just do a two-bubble Venn diagram. So two circles there. And we'll saw this set A and this set B. And over here, I'm going to write out the sets A and B. So we'll look, I don't know what letter we're on, D or E. We're on example E. We'll call this example E. Since we're going to put some numbers there. So set A is the numbers 3, 5, 7, 9, 11, and 13. So it looks like the odd natural numbers from 3 to 13. Set B, let's do 6, 8, 10, 11, 13, 14. So just a random choice of numbers there. And if we're going to put that into a Venn diagram, what numbers are going to go in the football shape in the middle? And why would they go there? Why do they go in there? They're in both sets. They're in the overlap, okay? And then set A, this bubble would contain all the other numbers that are in set A that are not in set B. That'd be 3, 5, 7, 9. All those are in set A. Set B, we got 6, 8, 10, and 14. So what we have here is an overlapping set. That overlap is called the intersection. Of set A and B. So a Venn diagram can be helpful in seeing that. Now, let's get some notation out of that. Well, how do you write the intersection of set A and B? A intersect B. So it's like an upside down U. That's what that is. Upside down U. Is this subset of 11 and 13. The intersection is the overlap. What's in both of them? That's an intersection. Okay. Intersection is in both of them. There's another thing called a union. It's the complete list of all elements in, usually it's just two sets, both sets. So if we looked at this and we said A union B, so it's the letter, it's like a big U. Makes sense, right? A big U, and the intersection is turn it over for the overlap. So the intersection would be, okay, all the numbers that are in A and B. You know, like that means every that's in the A or B. So got 3, 5, 6, 7, 8, 9, 10. There's the 11, the 13. It was the intersection, and then the 14. I'll scroll up so you can see that. The union is in A or B. Union is an or. Intersection in A and B. So it's the intersection's a more exclusive group. Okay? Think about, I always use this example when I talk about this with my high school students. Adamsville is a one red light town. Parsons used to be, it's not anymore, but it used to be. And that intersection there, that little square of property is the only place where those two roads that cross intersect. That's the only place that's both roads. When you're sitting in the middle of that intersection, you're not on either road, you're on both of them at the same time. So that's that intersection. And we call it an intersection when we talk about driving. And so that's that idea. We don't have much of an example of a union as far as that goes. That would just, I guess, be your map. It has all of the roads on it that you could be on from there. But the intersection is where they overlap. Really easy concept, okay? So let's take that, do a few examples. If we're given sets, so example F, let's call this set set W is 9, 15, 25, and 36. Set X is 15, 20, 25, 30, and 35. So I'm just picking some numbers here. And I want to first find W intersect X. What's the intersection of those two sets? 15 and 25 are in both of them. We got a 15 over here. We got a 25. That one X has both of those. There's nothing else that they share. Okay, so that's the shared pieces. So 15 and 25. Okay. Part 2. Let's do W union X. What's that create? Smaller set or a bigger set? Bigger set. Unions are going to create bigger sets than intersections are. So if we join these two together, we got the 9, and then there's that 15 that's shared, and then there's the 20, and then the 25 that's shared, and then the 30, the 35, and then the 36 from set W. I put them in numerical order just because I'm a little bit OCD. And if it doesn't really have to be that way, but there's just this weird tingling sensation if they're not in that order that just kind of bugs me, and I would have to go back and fix them. So they don't have to be in numerical order. You will see them in numerical order on tests and quizzes, though, just because that's the way most mathematicians do that, just because it makes sense, right? Why would you not? Okay. Let's take set G is 1, 3, and 5. We'll do a small one here. And set H, 2, 4, and 6. What's the intersection of those two? There's not one, right? There's nothing that's shared between them. So that would be the what? The null set, the empty set. Yeah, those are the same things. So I would accept either this or circle with a slash through it. Either of those would be absolutely fine with me as far as how you write that. Know that they mean the same thing, because on quiz or a test, or when you look in your book for practice problems, they may do the empty set, or they may have the circle with the slash through it that way. They kind of bounce back and forth with this book, which notation they use. The number theory that I've done always used the empty set like this, but the other is also accepted, so it's not like it's anything crazy. All right, now let's talk about another thing in sets. It's called a complement.
So if there's no intersection, then you don't do the union.
Well, I just didn't ask you to do the union. You could. It's going to ask you to do one or the other, or
So like if it was on a test and it didn't have an intersection, you
then
still do that, but you do the union too.
not necessarily, not unless it asks for it.
Well, that's what I'm saying. If it asks,
If it asks you for both of them, then yeah, you could still do a union, but there's no intersection here. There could be a union. There always can be a union, but there's not an intersection here. So it depends on what it's asking for. Usually, it's only going to ask for one or the other on a test. As far as that goes, I'm not going to ask for both usually on a quiz or a test. All right. Complement with an E in the middle, not an I. Complement not like I like your shirt. Complement like in math world. Okay. The complement of a set. It's the elements that do not belong to a set. Normally from a universal set, a universal or larger set. That's given. So they're going to tell you, hey, we're talking about the natural numbers here, and the complement of and they give you a subset of the natural numbers, and you're supposed to come up with the complement of that, which would be the things that are not in your set, that sort of thing. So complement are the elements that do not belong in a set. So let's get a few examples here of this. I don't know what letter we're on. H. Example H. I'm going to define a few sets for you here. 1, 2, 3, 4, 5, 6, 7. A nice, easy set of natural numbers there. And then set B, let's say it's 1, 3, 5, and 7. And set C is 3, 4, and 6. Okay? So those are the sets that are given. Okay? They give us those sets. And then what we want to look at here, I want to answer a few questions. Number one, is B a subset of A? Yes. Number two, is C a subset of A? Yeah, 3, 4, and 6 are all part of set A. So what's that tell us about A? A is the larger set here, right? It's got more elements in it. The other sets that they told us about are subsets of that. So we could think of A as maybe our universal set for this particular problem because it's the larger set that these other two that they told us about were subsets of. Okay? So the third question I want to answer in this is this. And it's B with a little apostrophe there. And, you know, B prime is how that's read. But what it means is the complement of B. So if B is 1, 3, 5, and 7, the complement of B would be the parts of the universal set that are not in B, which would be what parts? 2, 4, and 6. That would be the complement of B. It's the elements of the larger set that are not in B. So you see that B prime, B with an apostrophe on it is what it looks like. That means it's the complement of B. What's not in B? It's in the universal set. Okay? What about C prime? C is 3, 4, and 6. 1, 2, 5, and 7. Good job. Not too bad, right? Not too bad. Okay. In your textbook, in your textbook, there's a box on page 6 that talks about set operations. Kind of puts all of this into one box for you, of places that you can go. It'd be a good thing to try to maybe copy that down at some point, and it's everything we've done so far, but it's all in one box for you to kind of give you an overview of that. So that's a good little box to have. Maybe snap a picture of it with your phone so you got that handy when you're maybe working some practice problems out of that. So that's a good part of that section. So that's section R1.